Okay, welcome to this video on parallel, perpendicular, intersecting, and coinciding lines. Let's just graph these lines and see what the graphs look like. All of these lines happen to be in the form y equals mx plus b, right, where we know the slope and the y-intercept. Let's see, so let's start by graphing with the y-intercept. Let's do this first one here, y equals 2x minus 1. I'm going to do that in blue. So the y-intercept is -1, the y-coordinate is -1 there. Okay, and then the slope is 2, which means I'm going to go up 2 for every one that I go over. There's a second point on the line, and that means that it would look something like this, right? That's the line, the graph through those 2 points. Okay, okay. Let me do a different color to do the next graph. So for this one, right, we have a different y-intercept, 2. Okay, so this crosses the axis at 2. Has the same slope though, up 2 over 1. So up 2 over 1 makes the second point there. And so if I were to graph that, look something like this. Okay? Not quite right, but pretty close. Hard to graph accurately by hand on a smart board, something like that. Okay. Let's do another example here. Different y-intercept. This time it's 3, so this crosses right there. Still a slope of 2 though, so I go up 2 over 1, there's another point, and so I have another line like that. Okay, my graph isn't perfect here, but I'm hoping you can see something about this, right? When the slope is the same, then even though the intercepts are different, from those different intercepts, I still go up and over the same amount to get to the other point. So the lines all end up going in the same direction, okay? So if you were to graph it a little more accurately, actually this one is a +1, but yeah, let me change that to +1. Okay, so here are 3 lines that have 3 different y-intercepts, but they have the same slope. If they have the same slope, it turns out the lines are parallel, right? From geometry, we say when lines are going in the same direction where they never intersect, then we call those lines parallel. So if I have equations that are in the form y equals mx plus b, the slope-intercept form, I can just look. If I can see that the slopes are equal, then I know those equations are parallel. Those lines are parallel. Okay, so maybe I want to check, are these lines parallel? This on the left-hand side, are these two over here, are they parallel? Well, for me to check, I'd have to compare their slopes. They're not easy to work with yet because they're not in a form that I can easily see the slope, but I could solve each for y to convert them to slope-intercept form, so I could see that. Let's take the top one. Let's see, if I subtract an x from both sides, I'd have 2y equals -x plus 4, and then if I divide everything by 2, I get y is -1/2 x plus 2. And then let's look at the other equation here. So this is going to be 6y equals -3x plus 18. Just divide everything by 6 right now. We have y equals -1/2 plus 3. And since those slopes are identical, yes, these lines are parallel. Those lines are parallel. Let's take a look at the ones on the right-hand side. Let's see, we've got x plus 3y equals 4. If I were to force that to be in slope-intercept form, let's see, I would subtract an x. I would divide everything by 3. I'd get y as -1/3 x plus 4/3. Okay, and then this one, 2y equals -x plus 7. If I divide everything by 2, I get y as -1/2 x plus 7/2. And if I compare those slopes, one of them is -1/3 and one's -1/2. So that means no, these lines have different slopes, different slantiness, and therefore definitely not parallel. So the ones on the left were parallel, but the ones on the right were not. And for me to check, I needed to be able to find the slope, and the easiest way to do that is to convert to slope-intercept form so I can read that. Okay, so parallel lines. What about lines whose slopes are not equal? Let's graph each of these 3. Okay, here's a line. Let's see, y-intercept is 1, slope is 2. So that one looks roughly like this. Let's see, this one right here, y-intercept is -2, slope is +3, so up 3 over 1, so something like that, okay? And then this one, let's see, +4 for the intercept, 1, 2, 3, 4, -3 for the slope, down 3 over 1, something like that. All right, so these are definitely not parallel. So what do we call lines if they're not parallel? Basically, we call them intersecting. Those kind of lines are just called intersecting because they're intersecting each other. They're not parallel, they do intersect, okay? So in general, whenever slopes are not the same, you can just say that they're intersecting. However, there's some special cases. There's a special case of both intersecting and a special case of parallel, okay? Let's take a look at the special cases for intersecting. In general, lines intersect. That just means that they intersect at arbitrary angles. But if we happen to have two lines that intersect at right angles, then there's a special name for that. That means the lines are perpendicular to each other, okay? So I want to look at something related to the slopes. We know the slopes are not equal if the lines are perpendicular because they must be intersecting, right? So the slopes can't be equal. But maybe they're not equal in a specific way, okay? Let's take a look at the two slopes of these lines on the left. Here's a point, and here's a point, okay? So what's the slope there? It looks like we're going up 2 for every 3 that I go over. So the slope of this line right here, the slope is 2/3, okay? Let's look at the line the other direction. So here's a point, and let's see, here's another point right here. Looks like we're going down 3 and over 2, okay? So the slope of this line is -3/2. That's interesting. The slope of one line is positive 2/3, and the slope of the other line is -3/2. Well, I don't think we can conclude anything just yet, but let's look at another example here. So here's a positive slope line on the right. There's a point and there's a point. Looks like we're going up 1 for every 1, 2, 3, 4. So the slope of that line is 1/4, up 1 for every 4 over. And then the negative slope line, right, has this point and then maybe this point, right? So it looks like it's going down 4 for every 1 that goes over. So that would be -4/1. Now, just from those two cases, I think you can see the pattern, and it turns out that this is true for all perpendicular lines. If you look at two lines who are perpendicular, their slopes are what we call negative reciprocals of each other. In other words, one's positive and one's negative, and then they're reciprocals, so the fraction is flipped upside down. If one slope is 2/3, the other one is 3/2. If one slope is positive 1/4, the other one is -4/1. Right? So that's referred to as slopes are negative reciprocals. Okay, the reciprocal part means 1 over, right? The fraction's flipped, and the negative means one of them is the negative of the other one. One's positive and one's negative. All right, so that's a special case of intersecting. If the slopes are different, they're intersecting, but if they're negative reciprocals, then they're perpendicular. Okay? Okay, so special cases of intersecting. Lines with negative reciprocal slopes are perpendicular. And I can, if they're solved, I can tell right away if this is true, right? This slope here is 2/3 and this one is -3/2, so we could say this one is perpendicular. These pair of lines are perpendicular. And by the way, the geometry symbol for that is this, right? It looks like a little upside down T. And that would be true in this case too. This 3 can be thought of as 3/1, and this -1/3 is the negative reciprocal, so these ones are perpendicular as well. Okay. All right. What about the other special case? Let's look at these two lines here. Let's graph this first one. Y equals 2x plus 1. Let's see. So this has an intercept at 1, slope of 2. There it is. What about this other one? It's hard for me to graph it unless I put it in y equals mx plus b form. So let's get rid of the parentheses by distributing here and then subtracting a 1. Y equals 2x plus 1. Wait a second. That's the exact same equation as this one, which means that the other line is right on top of the other line. The two lines are the same exact line. When we have that situation, we call these coinciding lines, right? One line is coinciding with the other. Even though we think we have two lines, we really have two different equations for the same line. Okay, so you can think about it as intersecting at every single point on there. All right, to summarize it, let's look at all four cases. Okay, in general, most lines are just intersecting, right? If they have different slopes, like 1/3 and -2, like this first case over here, then they're just intersecting. They're gonna intersect somewhere, and one has, you know, they could both have positive slopes, both have negative slopes. One could be positive, one could be negative. But if they're different, then they're just intersecting. But there is a special case of intersecting. If they're different specifically so that one is the negative reciprocal of the other, like positive 1/2 and negative 2/1, then that means that not only are they intersecting, but they're intersecting perpendicular to each other. So they're perpendicular, okay? A very special case is if the slopes are exactly the same, but the y-intercepts are different. If that's true, then the lines are going in the same direction, but they're not on top of each other, so we call those lines parallel lines, right? And then a special case of parallel is if not only are the slopes the same, but the y-intercepts are the same as well, then it's really the same line, and so the lines are on top of each other, and we call that coinciding. Okay, I've got a few more examples here. I'm just going to work examples till we run out of time. Let's take a look. Are these lines parallel, perpendicular, intersecting, or coinciding? All right, so pause the video, see what you think. So it depends on slopes and y-intercepts, so we should probably convert both lines to slope-intercept form. Maybe by, for the top line, subtracting a 4x, so I can see the slope and the intercept. And then over here, maybe we get rid of parentheses, negative by distributing, negative 4x plus 4. And then if I subtract a 3 here, I get y equals negative 4x plus 1. So what do I got here? Well, I've got slopes that are identical. So these lines are at least parallel. And since the y-intercepts are different, then it's not the same line. We would say these lines are parallel. Okay? All right, let's take a look at another example. What about these lines? Again, we need to convert to y equals mx plus b form. Pause the video, try that, see what your conclusion is. Okay, 5x minus y equals 1. Let's see, I could subtract 5x from both sides. Negative y is negative 5x plus 1. And then maybe multiply everything by negative 1 to get a positive y on the left side. So that changes all the signs. So I have y equals positive 5x minus 1. And then for this one, I have x plus 5y equals 1. So if I subtract an x from both sides, I get 5y as negative x plus 1. And then if I divide everything by 5, I have x equals negative 1/5 x plus 1/5. Okay, let's look at slope first. This slope is negative 1/5. This slope is positive 5/1. And that means these are perpendicular. So these are perpendicular, because that's that special case where the slopes are negative reciprocals of each other. Okay, what about this one? Well, let's convert to slope-intercept form so we can see the slopes. Subtract a 5x from both sides. Negative 2y equals negative 5x plus 1. Divide everything by a negative 2. Y equals positive 5x, 5/2 x minus 1/2. Okay, over here, 3x plus 5y equals 1. Subtract a 3x. So I have 5y equals negative 3x plus 1. And if I divide everything by 5, I get y is negative 3/5 x plus 1/5. Let's look at the slopes. Negative 3/5, positive 5/2. Well, they're different, and they're not negative reciprocal, so I think I just have to conclude that these are intersecting. They just intersect each other. They're not parallel, they're not perpendicular. Okay, that's all the ones I had. This is the summary right here. There are 4 cases.